Good evening. I'm John Hunt. This is Jeff Badenoch, and we are doing short literary readings before these 6 lectures. It was Jeff's idea, and we got together to talk about what we would do over lunch, and we were looking at each other over our Thai food, and Jeff started going into rhapsodies about the scientific properties of water. It dissolves everything. It's H2O, very simple construction. You can break the hydrogen and the oxygen apart. You can recombine them with fire. And he's on about his 8th one, and I was thinking, I've got just the literary passage for you. It's from James Joyce's Ulysses, and it's about the scientific and other properties of water. So that's what we're reading. I'll just give a real brief introduction to these paragraphs. They come from the 17th chapter of Ulysses, which is set in the form of a Catholic catechism of question and answer. But the worldview is not very religious, it's much more scientific. At some point in the chapter, the 2 characters who make up most of the action of the chapter, Stephen Dedalus and Leopold Bloom, a question is asked of them, what 2 temperaments did they individually represent? Answer, the scientific, the artistic. The scientific temperament is Leopold Bloom. And this section takes place in his kitchen where he's about to boil water to make cocoa for his guest. So, several questions and answers.
What did Bloom see on the range?
On the right, smaller hob, a blue enameled saucepan. On the left, larger hob, a black iron kettle.
What did Bloom do at the range?
He removed the saucepan to the left hob, rose and carried the iron kettle to the sink in order to tap the current by turning the faucet to let it flow.
Did it flow?
Yes. From Roundwood Reservoir in County Wicklow, of a cubic capacity of 2,400 million gallons, percolating through a subterranean aqueduct of filter mains of single and double pipage constructed at an initial plant cost of £5 per linear yard by way of the Dargle, Rathtown, Glen of the Downs, and Callowhill to the 26-acre reservoir at Stillorgan, a distance of 22 statute miles, and thence, through a system of relieving tanks, by a gradient of 250 feet to the city boundary at Eustis Bridge, Upper Leeson Street, though from prolonged summer drought and daily supply of 12.5 million gallons, the water had fallen below the sill of the overflow weir, for which reason the borough surveyor and waterworks engineer, Mr. Spency Harty, C.E., on the instructions of the Waterworks Committee, had prohibited the use of municipal water for purposes other than those of consumption, envisaging the possibility of recourse being had to the impotable water of the Grand and Royal Canals, as in 1893, particularly as the South Dublin Guardians, notwithstanding their ration of 15 gallons per day per pauper, supplied through a 6-inch meter, had been convicted of a wastage of 20,000 gallons per night by a reading of their meter on the affirmation of the law agent of the corporation, Mr. Ignatius Rice, solicitor, thereby acting to the detriment of another section of the public, self-supporting taxpayers, solvent. Sound.
What in water did Bloom, water lover, drawer of water, water carrier, returning to the range, admire?
Its universality, its democratic equality and constancy to its nature in seeking its own level, its vastness in the ocean of Mercator's projection, its unplumbed profundity in the sun-dammed trench of the Pacific exceeding 8,000 fathoms, the restlessness of its waves and surface particles visiting in turn all points of its seaboard, the independence of its units, the variability of states of sea, its hydrostatic quiescence in calm, its hydrokinetic turgidity in neap and spring tides, its subsidence after devastation, its sterility in the circumpolar ice caps, Arctic and Antarctic, its climatic and commercial significance, its preponderance of 3-to-1 over the dry land of the globe, its indisputable hegemony extending in square leagues over all the region below the sub-equatorial Tropic of Capricorn, the multi-secular stability of its primeval basin, its luteal fulvus bed, its capacity to dissolve and hold in solution all soluble substances, including millions of tons of the most precious metals, its slow erosions of peninsulas and islands, its persistent formation of homothetic islands, peninsulas, and downward tending promontories, its alluvial deposits, its weight and volume and density, its imperturbability in lagoons and highland tarns, its gradation of colors in the torrid and temperate and frigid zones, its vehicular ramifications in continental lake-contained streams and confluent ocean-flowing rivers with their tributaries and transoceanic currents, Gulf Stream, north and south equatorial courses, its violence in seaquakes, waterspouts, watersheds, water partings, geysers, cataracts, whirlpools, maelstroms, inundations, deluges, cloudbursts, its vast circumterrestrial horizontal curve, its secrecy in springs and latent humidity revealed by rhabdomantic or hygrometric instruments and exemplified by the hole in the wall at Ashtown Gate, saturation of air, distillation of dew, its simplicity of its composition, 2 constituent parts of hydrogen with 1 constituent part of oxygen, its healing virtues, its buoyancy in the waters of the Dead Sea, its persevering penetrativeness in runnels, gullies, inadequate dams, leaks on shipboard, its properties for cleansing, quenching thirst and fire, nourishing vegetation, its infallibility as paradigm and paragon, its metamorphoses as vapor, mist, cloud, rain, sleet, snow, hail, its strength in rigid hydrants, its variety of forms in locks and bays and gulfs and bights and guts and lagoons and atolls and archipelagos and sounds and fjords and minches and tidal estuaries and arms of sea, its solidity in glaciers, icebergs, ice flows, its docility in working hydraulic mill wheels, turbines, dynamos, electric power stations, bleach works, tanneries, scotch mills, its utility in canals, rivers, if navigable, floating and graving docks, its potentiality derivable from harnessed tides or watercourses falling from level to level, its submarine fauna and flora, anacoustic, photophobe, numerically, if not literally, the inhabitants of the globe, its ubiquity as constituting 90% of the human body, the noxiousness of its effluvia in lacustrine marshes, pestilential fens, faded flower water, stagnant pools in the waning moon. Any questions?
Wow, who would have thought? From making hot cocoa. It's quite amazing. It's my joy today to welcome all of you to the 4th lecture in our series on Western rivers, connecting landscapes and livelihoods. I want to remind everybody to turn off your cell phones. I want to remind everyone that there's still art on display from the Montana Museum of Art and Culture over in the Mansfield Library and also in the President's office. So if you have a chance during opening hours, go over and take a look at that water. And I wanted to mention to you, I don't like to bring this up too early in the series because people kind of get impatient, but I do want to assure you that we're having our usual annual reception after the last lecture. So it will be there. We'll all have some kind of food. I don't know whether Bill Woesnner is going to have to catch fish for us or what. Last time we had Russian food of some kind. But in any case, I hope you'll all just come and take part in that. It's always a lot of fun to chat with our lecturers and get a chance to put the whole series together. As I did of everybody else, I asked Bill to let me know how he became interested in waters, and it sounded as though he had one of those lives where you could say a river ran through it, although it was maybe a creek or a lake or a sound or something like that. But what attracted me to his statement was that, and I thought, on what small things our fates turn. He said that as he was graduating in geology from college, he happened to read a paragraph in a geology textbook about land water, groundwater, and groundwater resources and so on. So he just thought, well, that's something that concerns everyone. Why don't I be an hydrologist instead of an oil man or a gas man? So in any case, there we are, one little paragraph in somebody's book, and we have Bill Woesnner with us ever after, and I'm really glad of that. Bill's worked on lots of projects in his career, which it seemed to me to have to do with groundwater and some of the biggest issues we deal with every day, like mining, like nuclear waste, disposal of nuclear waste, and so on and so forth, and how these affect our groundwater. And basically how groundwater, once he was here in 1981, how groundwater works with rivers, intersects with rivers. Bill is, as you know from your program, I try not to repeat too many things that are there, but he's been a Regents professor at this university for several years, I think since 2004. I think we have at least 2 other Regents professors here, so I'm really glad to see them, Jackie Moore and Paul Lauren, and these are really the best of the best, so they're a real treat. I myself have known Bill as a strong advocate for faculty. He's trying to tell me to sit down and shut up. And then he's going to hide behind here. But in any case, all right. So he's the professor, I'm not. Thanks, everyone.
I'm not sure what you're in for today here, though. You know, I was listening to the reading, and the first thing I thought was, where's the groundwater? I heard well and I heard spring in there someplace. But that's really what we're going to talk a bit about today, is trying to look at landscapes and rivers and groundwater, and especially groundwater and rivers. So when I see a scene like this, the scientist, the hydrologist, looks at this and they say, well, you know, I think about great literature and I think about great art when I see a scene like this. And I think about history and culture, the cultural aspects of a scene like this. And I even might think about the law, especially if I'm not supposed to be there, you know. But in reality, what the scientist, the hydrologist, looks at is this question up here. Is that, well, where is the water coming from and where is it going? And really, that's what it's all about when we think about the hydrology of a landscape. And we're going to look at that today. This evening, and we always, all hydrologists, I'm a groundwater hydrologist, we all have to start with the sort of the water cycle, and we think about what goes in and what goes out of the landscape. And I think, you know, pretty clearly you often think about rainfall, and it hits the land and it runs off the land, and then it forms a river down here. And this river that we have then is flowing away here, and we think about the rainfall that must have helped create that river. But we also know that, of course, some of that rainfall makes it to the land surface, and it works its way down deeper into the system. And then we have a second component here, which is this line which represents something called groundwater, which is another feature which is also feeding the stream. So that's what we're going to really sort of talk about today, are those different aspects of how groundwater and river systems actually interact. So here's my plan of attack, right? We're going to spend just a little time talking about groundwater systems to sort of get all on the same page. And then we'll look at the principles of sort of how groundwater and surface water, groundwater and rivers interface and interact, and the complexities and the various scales of those things. And then we're going to look at some applications. And it seemed like some reasonable applications were to look at rivers, and in this case, the Missoula Aquifer, and look at rivers and look at Milltown, which is, again, just a few miles out of town. So we're going to take what we've learned and basically apply it to these two features, the Missoula Aquifer and the Milltown Dam removal. So we start out with just the idea of what groundwater is. And, you know, when I ask that in my class, the first response is always, it's water under the ground. And that's correct, except it's not quite scientifically correct, because scientifically, to be correct, it's water that is in what we call the zone of saturation. And the surface of that zone of saturation is called the water table. So the water percolates down and forms the groundwater system. So imagine this room now full of bowling balls. Okay, I fill the room up from top to bottom with bowling balls, and then I turn on the hose, and I fill the room up halfway with water. Right? So now I have the bowling balls, in between the bowling balls, there's water there, and then there's this surface which represents the filling to the middle of the middle of the room. And that would be the water table, and the saturated zone would be the water all surrounding those bowling balls from the middle of the room to the floor. So if you think about it, that's what a groundwater system is, and that's as we define it, it's the water in the zone of saturation. Okay? Now, you have to stay awake today, because I now have a question. I want you to define an aquifer. What is an aquifer? Now, if you want to be here till 10:30, you can just sit there. But if we want to get going here, I need a couple of responses, so just sort of shout out and I'll repeat. What is an aquifer? We always talk about aquifers, the Missoula aquifer. What is an aquifer? What's the definition of an aquifer? Something that carries water. Another idea. That's partly correct, right? What else? Yes? An underground reservoir. So that implies storage somehow too, right? What else? Reservoir, another reservoir. Anything else? Definition of an aquifer. You all know what it is, right? You read about it all the time. What is it? What is that? A source of water. Okay. So we've got most of the components of that. And if we look at a definition from a scientific point of view of an aquifer, it's saturated earth material, that zone of saturation, right, where the pore spaces are all full of water, and it stores, transmits, and it economically yields waters to wells. Oh, isn't that interesting, right? So that's what an aquifer is. It has those components. So we can actually have zones of saturation or groundwater which are not aquifers. In this case, we may have what we call an unconfined aquifer. It has the water table. Here's the zone of saturation. That's our bowling ball, our room full of bowling balls. But if we go down to the basement of the building, let's pretend there's another room full of bowling balls down there, and it's totally saturated. And that's a second type of aquifer that we might call a confined aquifer. So maybe we could get water out of it too. But in between, there's a bunch of stuff here like shale or granite. Doesn't have much ability to store or transmit water. So even though it's full of groundwater, we wouldn't consider it an aquifer. And we'll look back at that, about that economic issue in just a minute. How about groundwater storage? Well, we just talked about that. The bowling balls in the room, half the room full, half full of water. That means we're storing water in that half of the room, in between those pores, those pore spaces, those empty spaces between the bowling balls, right? Well, we can change the amount of water stored in this room by making the water level go up or down. And that's exactly what happens in a groundwater system when we have the water table rises up during part of the year or falls down. We're putting water in storage, or we're taking water out of storage just by the change in the water level, the change in the position of the water table itself. Okay? Groundwater, it transmits groundwater, so groundwater moves. We always think of things that we hear about the groundwater reservoir, and we imply, well, maybe that means it's static. It doesn't go anyplace, it just fills up and empties and fills up and empties. But it doesn't, it moves. And the reason that it moves is that it moves from areas of high water table to areas of low water table. So where the water table is highest in elevation, it wants to move from that point to a place where it's lower than elevation. So imagine our room full of bowling balls, right, and the water's filled up halfway through the room here, and now I take the floor of the room and I tip it up. And now the water table is higher in the back of the room than it is in the front of the room, so the water is going to want to move from the back of the room to the front of the room. And the way we figure that out is we drill wells down and we figure out where the water table is, and then we drill a number of wells, and then we plot up the elevation of the water table, and this is like a plane surface here, higher over here, lower over here, and then we just draw a line of groundwater flow which traces out the direction the groundwater will go. So it's really quite easy. All we need is a bunch of holes to look at the elevation of the water table and plot it up, and we can figure out which way the groundwater is moving. So here's an example of that. So we have a situation where we have a river flowing through the area here, and we've drilled a bunch of wells, and these happen to be in meters, but these are elevations of the water table from measuring them in all of these wells. And the next thing we do is we just make a contour map of the water table, just like a topographic map of the land surface when you're hiking that shows you the difference in elevation. This shows you the difference in elevation of the water table. And we just contour up lines of equal elevation of the water table. And then we just plot lines on that map that go from high elevation to low elevation of the water table. And so this tells us the actual direction of groundwater flow. Again, it's pretty easy once you have that first piece of information. What does that surface look like. And then to think about groundwater, how old is that groundwater? How long does it stay in residence? How fast does it move? Well, we measure groundwater velocities in terms of feet per day, feet per month, feet per year, like 1 foot per year. It could be groundwater flow. Could be 1 foot in 1,000 years in some groundwater systems. So this sort of illustrates that short flow paths have maybe in the units of days, longer flow paths in the units of years. It takes a year to get that water to move from some place over to a place like a stream. Or if we have very deep circulating, we can have thousands of years that the groundwater can be in the system for thousands of years before it comes back out. And it's kind of interesting, you see the stream over here, it's receiving groundwater of all different ages, different pathways, different lengths of time in the system. Economically yield water to wells. Well, how does a well work in a groundwater system? Right? So if I put a well in the middle of my groundwater system I built in the room here, and I turn it on and start pumping water out of the room, what will happen is that at the well location, I lower the water level. And because I lowered the water level, everything around it is higher, and what's the rule? Groundwater flows from high water table elevation to low water table elevation. So it basically will move to the low spot, and then we can keep pumping it because it starts to flow to the well. And this is just an example of that here's a well that's not being pumped. The groundwater is flowing through here. These purple lines are equal water table elevation, so it's just flowing right on by. And then here we turn the well on, and it starts to capture the water that's moving along through the system, and we change the shape of the water table, and we have water moving towards the well. Now, if you're living out in the rural area and you have a household well, and you turn the well on and use it, maybe you get 10 gallons a minute. And you're tapping an aquifer. For you, that's economically efficient to take that 10 gallons a minute out of that well that you have for your house. But that in your case, that would be an aquifer that you were tapping. But if I was building a power plant out there, and I needed 4,000 gallons per minute, and I couldn't get it from the aquifer that you were using, I would say, oh, that's not an aquifer. I need to go find one that's deeper or bigger because for my use, my economically viable use, it's not an aquifer. So this sort of clouds the issue a little bit about how we define the term aquifer. But for most practical purposes, we can think of groundwater systems as being aquifers because they're sort of referred to as that they're storing, transmitting, and they're yielding water to wells. But not all saturated material are aquifers. So that's the background material, okay? And so a groundwater system. So now we've got all these pieces of how groundwater works. And in a groundwater system, we basically have what we call groundwater recharge. And that's that we put water into the groundwater system from rainfall, snow melt. We percolate water through the soil zone, and then it enters the saturated zone of groundwater. And then it flows along through the system, and then it comes out and it discharges. So the second part of the system is where it comes out. We call that groundwater discharge. So we have groundwater recharge area, groundwater discharge area, and then we have flow in between. And if we want to change the storage, all we do is have to make the water table rise and fall, and we will add water or take water out of that groundwater system. So that's the first piece of sort of basic background information about what groundwater systems are and the main features of them. We're going to keep seeing them again and again as we continue on with some other aspects. So we're on the second part of the progression here. And the second part is how are groundwater systems and rivers actually interconnected? Okay? So, okay, everybody wake up. Another question? Okay? Tell me what you see in this picture. Surface water, river, what else? Rafters, thank you. Okay, right? So that's what your image is when you see that, right? So how about this one? What's that? A bridge, right? What else? What do you see there? Trees. Stream. What was that? Feed lines, yes, trout fishermen. Feed lines on the water, okay? Well, that's all true, but it's not what I see. Because what I see is I see surface water that actually originated as groundwater. So it is surface water. That's how we define it. It's on the surface of the land. But its source is groundwater. In both of those situations, and in many more. Okay? Well, you might ask, now, wait a minute, how does that work? Well, let's look at the hydrograph of Rock Creek. So here is the discharge of Rock Creek over here, 100,000, 6,000. Here is the time, January 2010, July, January, July. And so this is the flow in the stream at the place where they watch the flow down near the mouth. And you can see that in the wintertime it's kind of low. And then here comes spring runoff and snow melt, and it jumps way up. And then it drops back off again. And then from the fall on, there's sort of this sort of strange-looking thing, but there's a bunch of water still flowing down the river, but there's no more snow or rain. And then the next year it repeats itself, and then wintertime it sort of gets low and keeps going like that. Well, you might ask yourself the question, if this is what Rock Creek looks like in the dead of winter, it's 20 below zero, and there's water flowing down Rock Creek, where's it coming from? Why is it in the creek? Right? Why is there water in the river? And the answer is because it's groundwater. So groundwater is coming out of the rocks and the watershed, and it's feeding that stream, and it's doing it all year round. So this is an example of that during the wintertime, it's almost all groundwater discharging from that groundwater system in the mountains into the river system. And then during the runoff, you get a little more input, but this is all surface water. This is rainfall and snow melt running into the system pretty much. And then it drops back down, but this is basically what we call base flow of streams. And the base flow of a stream is groundwater that's discharging to the stream. So immediately, hydrologists say, oh, certainly there's a connection between surface water and groundwater, right? Because we see this all the time when we look at stream discharges. You look at the Clark Fork River. Before we had all the snow melting and stuff, why is there water in the Clark Fork River all winter, right? And in the fall, when it hasn't rained for months, right? So keep that in mind. So now we're going to go to the scale of thinking about river systems and basins. So this is the big scale, where the length of river in a basin might be tens to hundreds of miles, like the upper Clark Fork drainage, for example. And so what happens, what are some of the possibilities as far as groundwater, surface water interaction here? Well, here's our stream coming down the basin, flowing in this direction. And then if we measure the discharge, the amount of water in the stream here, and then we go tens of miles downstream and we measure the amount of water down here, right? If there's an increase in the stream flow, then we call that a gaining stream. It's gaining flow from up the high elevations to the low elevations. And in this case, if it's mainly groundwater that's being fed to the stream. So for that to happen, you have to have the stream level here. You have to have the water table sloping away from the stream but being higher than the stream stage. And so the groundwater goes from high elevation to low elevation. The stream is the low point, and it starts discharging and feeding into the stream. So one option we could have is that overall, that stream is actually gaining groundwater. So we call it a gaining stream. Of course, then we could have the opposite. We're out in a desert or arid environment. We measure the flow in the same location in the basin. We measure it further down. And this time, we find there's less water in the stream. And that's called a losing stream, right? We're losing flow. And the reason we're losing flow is because the stage of the stream, the elevation of the stream, is higher than the groundwater system next to the stream. So it's trying to push its water out away from the stream and into the basin system. So that would be called a losing stream. Okay? And this is on this scale of the big scale, right? Well, then we can change scales again. If we think about this groundwater, surface water interaction, we now move down to sort of the reach scale, which let's say it's hundreds to 1,000 feet in length. And so you might have, this is Elk Creek up by Lubrecht Forest here, coming down through Paws Up, and you have the creek winding along here, and you have maybe a floodplain area of about 100 feet, or you could have a river running along here. Here we have a couple of miles of floodplain. And what we would find is that the sediments in here, in the lower part, in this flat part, the yellow part, would be mostly sands and gravels and clays that are laid down by the river. They're left behind by the river. And as you get outside of that area, you go up into the hills, and you may change the composition of the material. Maybe it's a finer grained material, or it's rock or something else up there. And so what we want to know is that how is the groundwater and surface water exchanging on some reach of the river here? is it more complicated than those simple things that we set out? And how would we figure that out? Well, we drill a bunch of wells in the floodplain, and we'd plot up the elevation of the water table, and we'd measure the stream flow and measure the height of the water in the stream and compare it to the groundwater. And this is an example of that, where you see these are the lines of equal elevation of the water table. This says 100, and this one down here says 75, so it's higher water table elevation, lower water table elevation. So the black arrows are groundwater flow lines and how they're interacting with the stream. And when we study this, which we've done in numerous streams, we find out that there's a number of options of how the groundwater and the streams might actually interact. Well, the first one is what we already talked about. So we could have a stream channel, and right next door, the water table is higher than the stream channel on both sides, and the water is trying to flow and discharge to the stream, so we'd have a gaining stream. We'd be trying to increase the amount of water in the stream as it was moving along and flowing down through that reach. Okay, so that's one option. Then the second option is, well, we could have a losing stream in that reach, right? It could be a losing stream. And we said, here's the example we used before. Here we have a stream elevation is higher than the water table, and they're all connected, and the water's seeping out of the stream and away from the stream and losing its flow, recharging the groundwater system. But we could have this other example here where we have the stream which is flowing along, and it's actually suspended or perched in the sands and gravels or clays above the water table. And the only way the water is going to get out of there is to percolate from the bottom of the stream, to leak down into the groundwater system, which is actually below the stream itself. That's pretty interesting, right? Well, then we might as well have something like this too, though. So we could have a situation where the stream channel is here. We have the water table higher on one side, so groundwater flows in this bank of the river. And then the water table on the other side is lower, so the river water flows out of the stream and goes out into the floodplain. And we call that a flow-through section of stream. So groundwater is coming in one bank, but river water is seeping out and continuing on through the other bank. And then finally, if we looked at all the possibilities, I guess we could have a situation where the water level in the stream was exactly the same as the water level in the groundwater, and there was no gradient. There was no way to move water between the two. So all the flow would just have to be parallel to the stream. Okay, so let's put all these things together. Oh, well, first we'll show some examples. So do these things really exist? So here's Little Spring Creek up by Ronan, and here's Spring Creek here, and this is the water table up towards 93, and this is the water table off the other side. And we had a contamination of the groundwater there, which was full of gasoline additive called MTBE. It's all contaminated. And when we drilled wells and we studied the system, we could see this chemistry only present here, and it all came up and discharged to the stream because the stream was a gaining stream. So all the flow was coming and discharging into the stream from both sides. And that chemistry just showed us that by actually studying that particular setting. And if we look at a losing reach of stream, this is the middle fork of the Flathead River. I've worked in this area for quite a while with the biostation. It's about 8 miles west of West Glacier, and the middle fork flows along here. Glacier National Park is right here. The river flows to the northwest here. And when the channel, where the river's flowing this direction, when the channel comes up against the bank here, the water table is lower in the floodplain than the river channel, and what we get is losing water out of the stream, and we see the stream chemistry, and we see everything of stream water going off into the groundwater system. So there's an example of a losing stream. And the flows-through stream, this is Silver Bow Creek up near Butte. Before it was reclaimed, this is mine tailings. All these are mine tailings from the smelting and mining up in Butte, and it washed out onto the floodplain. It's full of metals, and it killed all the vegetation. And so here's an example where we were studying what was happening geochemically here with my colleague Johnny Moore. This is mine tailings here on both sides of Silver Bow Creek, and the groundwater flow is from this bank into the creek, and then from the creek into the groundwater. And when we look at the cross-section here, we can see what's happening. Here comes the groundwater. The groundwater has a pH of 4, very acidic, full of metals, full of contamination. It slowly seeps into the stream, and it starts changing chemistry as a little bit of the stream water starts mixing. Then we get into the stream water, and the stream water has a very different chemistry. a more basic pH, it starts to leak out and move through the system and slowly changes back into that contaminated water. So there's an example of where a flow-through stream actually occurs, in the real world. So that means when we look at a reach of a river, it could get pretty complicated. It doesn't have to be all gaining and all losing, but it can be, and it usually is, pieces of both of those, or all kinds of those four possibilities. So here's an example where we have, again, the river is flowing in this direction. We have a losing reach of the stream here. We have a parallel flow of the stream here. We have a flow-through reach of the stream here. This is very common when the stream makes a right-angle turn across the floodplain. You get these flow-through conditions. Then we have a big gaining reach of the stream. We have another flow-through reach of the stream. We have a parallel flow, a gaining stream. Now, overall, if we looked over 10 miles, maybe this is all gaining. On the average, mostly it's gaining water, but all of these things are happening in between. And this gives you thought about, well, if you have a stream that's damaged and you want to restore it into a natural condition, do you have to reproduce something like this? Because that's what it really looks like under most scenarios. It's not just all one or the other, especially out west here in our system. And then I threw this in because Michelle was talking about this last week. She was talking about what happens when you pump a well near a stream, what happens to the flow in the stream, and her discussion was about water rights. So if all of the water rights are assigned for the surface water, and you own this property up here and you put in a well, the groundwater is trying to flow to the stream, so it's a gaining stream, and then you turn the well on. Remember what happens, you change the shape of the water table, you lower the water table, so now you start collecting the water that's coming in towards the well, and you start collecting some of the water on the other side of the well, but early on, there's still water flowing to the stream. You haven't affected this part of the water table yet. But after long terms of pumping, you actually can connect the water table up to the stream, and you're directly drawing water out of the stream to feed your well. So this becomes the issue of trying to use groundwater when you have surface water fully appropriated. Because when you start taking the groundwater, you're actually taking the surface water. And so that becomes a very interesting issue. Now, of course, it gets more complicated than that, just to throw that out for you to think about, right? What if the stream is perched up and losing? And then you start pumping the groundwater. Well, the groundwater is down below the stream. It's not connected to the stream flow at all in that case, so it's not going to have any effect right there because it's not connected to the stream. So that could be another scenario. And so if you look at our situation down here of our multiple area, if we put wells in different locations and we're pumping them, we might get very different responses in how the groundwater system and the stream system changed in response to that pumping. So that's food for thought, right? We could talk a whole day on just what really goes on there. But we have to just take one more step down in scale of groundwater surface water exchange. And this is the scale where the biologists get real excited. And Lisa will be talking about some of this next week, right? Because this is where we have surface water and groundwater mixing, we have nutrients exchanging, we have fish making choices because of that groundwater surface water exchange. So in this case, we have a channel, and in the channel there's obstructions, like there might be a bar, there might be some rocks or logs piled up in here, and we have some topography on the bottom of the channel, a riffle section, and then a pool, deeper pool section. And what happens here is that groundwater is trying to come up and discharge to that section of stream. Now maybe it's as big as this room, right? We're talking about something on that scale, right? But the surface water is hitting these obstructions and it's being forced into the riverbed and then popping back out again. So we're circulating water down into the riverbed that's stream water and then back up into the system. And then we're also trying to get groundwater to come in and discharge. Sometimes we can push it out into the floodplain a little bit and push it back in too. So this becomes quite interesting and gets even more complicated. And one example of that would be bull trout, choice of spawning areas, and how this surface water, groundwater come into effect. So here's a bull trout, and here's where they spawn. They work the gravels. It's called a red, and they lay their eggs in this. And it's pretty big. This is up in Glacier National Park. A student just finished his master's thesis up there. And we were looking at groundwater exchange and fisheries there. And this is about 6 feet in size. This would be where the eggs probably would be laid. But that's a disturbance on the stream bottom. And where that occurs is where the river water is being lost and being pushed into the bed. And it's right in the head of a riffle. So here's where you start a slope, and you start sort of like a little current, ripple marks coming down through here, and there's a deep pool. Well, right here, right as it drops off here, the river water gets pushed through this area here and comes back out, and that's where the fish decide to spawn. So the example here would be they would be spawning right in here, and that's where we find them when we go and look for where the bull trout are spawning. But they need one more thing. They often spawn only in sections of stream that overall are gaining. So the main groundwater system in the floodplain or valley is also trying to come in and discharge to try to come into that area. And they choose that because it moderates the temperature. The groundwater moderates the temperature of the river in those areas. So it's either colder than the river water or it's warmer than the river water, depending on what season you're in, and the fish choose those locations. If it's losing water and the river temperature is too cold, they won't spawn there, even if they have this type of habitat. So that's the reason why we get interested in these very small-scale issues. Again, what if we want to restore a river, fix it all back up so we have a better fishery? Do we need to reproduce something like this to have a good fishery as part of the deal? So this answers our second question, which was, how are groundwater and rivers connected? And the answer is, of course, intimately, right, and at multiple scales. So we've got the idea of our groundwater system. We have the idea of our river, surface water, groundwater interconnection. So the next task here is to look at some applications of this information or knowledge that we have, right? So let's make our first application to the Clark Fork River and the Missoula Aquifer. So another audience participation moment. Wake up again here, okay? So what do we need to know to protect the quality and the quantity of water in the Missoula Aquifer? What's percolating down? Where the recharge zone is. The stability of the water table. What else? Rattlesnake Creek. How does Rattlesnake Creek come into play? What else? What do we have to answer? What question do we have to answer? Where's the water coming from? And where? What question do we have to answer? Where's the water coming from and where is it going, right? I mean, this is critical to think about how the system works. We need to understand, as you've said, sort of how the system works. So let's take a look at what we know about the Missoula Aquifer. So first, all of the drinking water that you have that you use, if you live in the Missoula Valley or in most rural areas, all groundwater. In Missoula, 100% of our municipal water is groundwater. And it's designated a sole source aquifer by the Environmental Protection Agency. That was applied for by the City County Health Department back in the 90s, maybe, 80s, I can't remember now. But what that means is that they recognize for federal projects that the water is a sole source of supply. And they have to take that into account on their environmental impact statements and things, that they don't do something that might have an impact on this sole source aquifer. The sand and gravel in the valley bottom is the main aquifer. The geology is lousy for municipal supplies anywhere else or deeper. We'll see an example of that. And the water availability is going to be controlled by river leakage and water rights, okay, are going to control basically what happens with our water quality and quantity. So let's take a look first of since I have an opportunity here to teach a little bit, let's, and Don, some of my colleagues are sitting in the room and I'm going to be in trouble here because I'm a hydrogeologist, I'm a water person, but I want to give you a little bit of why the Missoula Valley looks the way it does, right? So let's look at the geological history of the materials that we have around the valley. The first one is about 1.5 billion years ago, there was big shallow lakes that were filling with sediment, very fine-grained sediment for, of course, many millions to billions of years, and we formed the rocks that we see in the hillsides. So Mount Sentinel, Mount Jumbo, all the big rocks that we see all around us, the bedrock is all very, very old material. And it formed when there was no vegetation and very different climate and everything else. So that's why you see this green and red type of stuff in the hillsides or gray rocks around. It's all very, very old, okay? Well, then we'll jump about 75 million to 60 million years ago, and we had tectonic forces pushing on this part of the world, and we formed the Rocky Mountains. We basically pushed up all of the rocks here, and then we started eroding them from that period on. And so from 50 million to 20 million years ago, it was pretty arid and dry, so it was more like, the example would be more like Nevada or Utah sort of environment where basins are closed and we have a lot of sediment eroding off the mountains, washing into the basins. And then what my colleague Jim Sears says, well, about 17 million years ago, things calmed down. We had wet and dry periods, but basically we didn't have as much faulting and basin building and that kind of thing going on. So that's, and the rocks, we're going to talk about, this is the bedrock. This is the stuff that's in the foothills and underneath of the valley floor. Deep part of the valley are the sediments left over from this time period. Okay? And then we jump ahead to the Ice Age, 2 million to about 10,000 years ago. And this is where we had lots of things going on. We had glacial Lake Missoula forming and emptying and forming and emptying. And we had lots of sediments being carried through and eroded and carried through and deposited in the valley. And so a lot of those sediments now, part of those have been reworked and make up what is the Missoula Aquifer today. And then today we have still evidence of those Lake Missoula stands. And this is the valley today with bedrock hills. And then the foothills over on the north and south have some of that older sediment in there. And then we have the valley floor. So that's sort of the growth and why the Missoula Valley looks the way it does today. It's those pieces that we put together. So if we draw a map of the valley, a very rough map of the valley, this is what kind of where things are and what things look like. So again, all of the mountains are the very old rocks. They're fractured, but they're not very high water yielding. They're certainly not municipal water supplies. And then we have those older sediments, which are sort of more the arid and wet sort of climates. It's quite different. Sometimes it was marshy and sometimes it wasn't. But these are, again, full of volcanic ash and other fine-grained sediments, and they're not very good water-yielding material. And then we have the sands and gravels and with some clay on the valley floor in yellow here, and that's the material which makes up the Missoula Aquifer itself. So this is what it looks like. You've seen it all in your backyard if you've dug down and run into those big cobbles or been down by the river, right? And so let's take a slice like a piece of pie from Blue Mountain over to Waterworks Hill. And if we did that, this is what we would find. We would find about 100 to 150 feet of coarse-grained sands, gravels, clays, boulder material, very coarse-grained material. And then underneath of that would be this finer-grained material that formed back, 50 million years ago to the present. And it goes down to 2,000 feet, and then it's on bedrock. So we have this fine-grained material underneath of that, but it's very poor water-yielding material. So we can't get into that for our water supply. If we took a slice from the campus here all the way down sort of towards Houston, we would find that the same thing, we have that same material underneath here, and we have the sands and gravels, and then we get out here near Frenchtown, and there's 100 feet of sand that is separating gravel above and gravel below, and they make shallow and deep aquifers out there that we can tap into. But that's what the composition of the Missoula Aquifer looks like and where it's located in the system. So this is the stuff we want to get our water from, and it's where we get our water today. So the next question is, where's it coming from and where is it going? How do we get water into the Missoula Aquifer, and where does it come out of the Missoula Aquifer? And this is a bit of a cross-section. This is that poor water yielding 2,000 feet of sediment. The Missoula Aquifer is up here. This is the water table. Here's Mount Jumbo, and so this is Hellgate Canyon. So where does the water come from? Well, we'd have some rainfall, right? Obviously it rains. We should get some of that water soaking in and helping add to the groundwater. Then we have Hellgate Canyon underflow, and that's right here. That means that we have groundwater coming from sort of up by Milltown, coming through Hellgate Canyon in the sand and gravel in Hellgate Canyon and out into the Missoula Valley. And I'll show you another sort of rendering of that to give you a feeling about what's that about. And then we have leakage from the Clark Fork River. So actually the Clark Fork River comes in here, and lo and behold, it's above the water table, right as it comes in through Hellgate Canyon. So it starts leaking water out of its bottom, and it recharges the groundwater system. And then we have a bunch of other things. We have rattlesnake, we have storm drains. All that water you saw running off in the past few days from the streets, those go into storm drains. Those storm drains are just simply grates on top of concrete rings with gravel in the bottom that goes right to the aquifer. So it recharges the aquifer. It doesn't get piped and go down to the river. It goes right into the aquifer as recharge. And then we have Rattlesnake Creek and Grant Creek. Same thing, sort of this underflow and leakage from those creeks, leakage from underlying sediments and adjacent sediments around the borders of the valley, like from the bedrock, water seeping in. But when you add up where all the water's coming from, what you find out is that 83% of the recharge to this eastern portion of the Missoula Aquifer is from leakage from the Clark Fork River. And 12% of the total is coming as underflow in that big sand and gravel package in Hellgate Canyon that's coming out and flowing into the valley. So the storm drains, they're less than 1% of the recharge, even though they look like they must be gigantic. They're tiny in the water budget. This is where all the water's coming from. Okay? Now, what are we talking about, this perched Clark Fork River? Well, if I go right down here to the walking bridge and draw a line across here and then take a slice and see what it looks like, what I'm going to find is that the Clark Fork River is actually up here, and then there's a bunch of saturated sand and gravel underneath of the river, and it's only about 2 feet thick. And then it goes into percolation. And the water percolates down. The water table is between 15 to 20 feet below the bottom of the river, right as the river comes in from Hellgate Canyon here. So it's perched up above. And so the water comes in, and then it adds to the groundwater system, and it flows away from that area. And Rattlesnake Creek is leaking too, and it does the same thing. It's perched above the water table system as it comes out of Rattlesnake Canyon and into the Missoula Valley. So this is what the gaining and losing streams look like around here. So here's the Clark Fork River. You notice this red means it's perched above the water table and it leaks water into the groundwater system. And we're going to see when we look at Milltown what happens up here. But basically it's all perched all the way through Hellgate Canyon and all the way down to about the sewage treatment plant. Right? So at that point the river level is actually higher than the groundwater and it's losing water into the Missoula Aquifer. Okay? And then below that area, Jacobs Island, it's gaining back again. So groundwater's flowing into the Clark Fork River in that area. And the Bitterroot River is also receiving groundwater discharge, and it's a gaining stream all the way down through the valley here as we look at this portion of the valley. You notice Rattlesnake Creek is also losing, except probably in Greeno Park. There's a little area here, I would guess, where there's some gaining. Groundwater's coming back into the stream, but as soon as it leaves that, it's going back out again. And the same thing on Grant Creek. Grant Creek's a big losing stream that comes out of the mountains. Okay? Well, the interesting thing is, of course, this isn't static, but in the springtime, as the water table comes up, because of all the river leakage gets greater and greater as the river stage gets higher, right? The river gets higher, we leak more water. Well, you actually move the shape of this, so in the springtime, that becomes a gaining reach for about 1 to 2 miles up above the sewage treatment plant. And then as the river flows go down, it migrates back downstream again. So it's actually transient. It goes back and forth in the system. What about this underflow concept? Well, the underflow concept is that here we are groundwater coming through Hellgate Canyon. So if we look at a slice right here across Hellgate Canyon, here's the university right here, we would see this. We would see the river, and we would see a saturated bunch of sand and gravel about 2 feet thick underneath of the river channel. And then we'd have percolation, and we'd have the water table. And there's over 240 feet of gravel and sand in the Hellgate Canyon. It's eroded down that far, and it's filled back up again. And so groundwater is coming through that coarse sand and gravel and coming out into the valley, and then it's going off and becoming part of the groundwater system. Okay? From that underflow. That's the 12%. Okay? How does groundwater flow in the Missoula Valley? Where is it going? Well, here we have the Clark Fork River, which is a recharge source, and we have water leaving the Clark Fork River as recharge into the groundwater, and the groundwater flows across the valley and discharges to the Bitterroot River. So on the south side, where we are right now, all the flow is from the river across over to the Bitterroot River, and here it's now coming down and discharging back into the Clark Fork. On the north side of the river, it flows along sort of parallel to the river and comes down again and tries to discharge down below the sewage treatment plant in that stretch of river. Some of it tries to keep going, and then the rest of the valley, it's just trying to get from the higher part of the valley floor area down to the river, so groundwater is coming in and discharging mostly from the valley sands and gravels and very little actually from the surrounding area here. So that's what the big flow system looks like. And if we think about discharge, Where's it going out of the system? Just to repeat that again, right? Well, these blue arrows are where the groundwater discharge would happen on the lower part of the Clark Fork River and all along the Bitterroot River, maybe some water trying to leave the valley. And then there would be municipal pumping, would be another source of discharge from the aquifer. We're taking water out of the system. But when we look at the total amount of water moving through the Missoula aquifer in this portion of it, we come up with about 75 billion gallons per year is moving through the Missoula aquifer every year, right? It's starting and throughout the whole year it comes out. That's the total that would come through the system in 1 year. Now we'll put that in perspective when we look at how much we're pumping out of the system, right? How much we're withdrawing out of the system. Okay, so let's talk for a minute about the water company, right? Our municipal water supply. This is a map of their service area, okay? And all those blue dots are wells. So this is the area in which they actually serve water. They have storage tanks and things, but this is where they take the water out of the valley. And this is how it sort of corresponds to our map of the Missoula aquifer. If we look at a blow-up of this, this is the location of their wells that they use, right? And you'll notice that most of them are scattered around here in this portion of the aquifer. It's all Missoula aquifer material. There's even a little bit coming out of the Bitterroot gravels here. There's a couple up in East Missoula. There's one up the Rattlesnake. There's actually one way out here by the airport, too. So this is what their service area looks like. And in 2012, I called them up and I said, how much water did you take out of the aquifer? And they gave me this number. And look at the precision of that estimate there, right? But it's very interesting. It's 8 billion gallons of water they withdrew. Well, that means then that about 12% of the natural water flowing through the system is extracted for water supply, for our use here in the Missoula Valley. So that's where that 75 billion comes in. Here's the 8 billion. So this is how much we take out every year and we use. Now, we don't actually use all of it. We put a lot of it in the sewer system, and it goes back into the Clark Fork River after it's treated and gets dumped back into the Clark Fork River. So it's not like we're consuming all that water. Well, in 2004 and 2005, the Mountain Water asked the question, what would happen if, when they remove Milltown Dam, they really mess up the quality of the Clark Fork River? Well, this could be important, right? Because we just learned that the Clark Fork River is a big part of the recharge to the water system, and if it gets impacted, it's going to impact the water supply. And they wanted to know, are we going to have to take these wells, these are big production wells, we're going to have to take these wells. There's another one out here we just used as an example. We're going to have to take them out of line because we won't have them to use because they'll get impacted. And so they said, where's the water coming from that's coming out of those wells, right? Where is it coming from? The river? Is it coming from the underflow? Is it coming from Rattlesnake Creek? And so we started a study where, again, we measured water levels in wells. All these, this case, all the blue lines are water table elevation lines. It's higher water table elevation here, lower water table elevation here. The dotted black lines are groundwater flow lines, right? The direction of groundwater flow coming from the river, coming from the north side of the river. And so what they wanted us to do is figure out this thing called the zone of contribution, or the capture zone. When we turn that well on and the water's flowing along, where's it going to get captured? Where's it coming from? How are we going to, if we trace that from the well back upstream, how far upstream does it go? Where's it coming from? Is it coming from the Clark Fork River? It'll stop when it gets up here, or is it coming from someplace else? So we built a three-dimensional computer model of the groundwater system in the Missoula Valley here, where we put all of the geology and all of our information inside the computer. We ran a code that did the physics and the mathematics, and then we dumped out the results, which showed us then how the groundwater moved in 3 dimensions. Okay? And then we said, okay, show us then from this system where the water's coming from. And so for this particular example here, we came up with something that looked like this. I'm not showing you a 3-dimensional rendering at this point. This is just a 2-dimensional map. But let's start over here. This is a production well that's out by the fairgrounds. Okay? And this is its zone of capture, is this purple line, which comes along and it goes up and it goes off the map. And you can see here that P26, 100% of the water that's being pumped out of that well is underflow coming out of Hellgate Canyon. It's not river leakage, not direct river leakage. It's coming from Hellgate Canyon, right? That underflow of water coming from upstream. Not the river, but the groundwater. And then we look at P30, which is over here. It's on the north side of the river. It's right over there, right about on Higgins Avenue, down there by the parking garage, right, on that side of the river. It's on the north side of the river. And when we look at that, none of the water is coming from underflow. Only 5% of the leakage is coming from leakage from the Clark Fork River. And look where all the other water is coming from. It's all Rattlesnake Creek water. So it's water coming out of leaking Rattlesnake Creek and the Rattlesnake Creek drainage. And it's very interesting because the temperature of that water and the chemistry of that water is different in that well. And it reflects Rattlesnake Creek water. Fascinating, right? And then we look at P32, which is right on the west side of Madison Street Bridge, just before you go over the bridge. And about 50% of the water comes as underflow, and about 50% comes out of direct leakage from Clark Fork River, right immediately from the Clark Fork River. And then P34 is always like P34. It pumps 7,000 gallons a minute for summertime when it's being used, right? That's a lot of water. And it gets 18% of its water from underflow, but most of it's coming from right there from the Clark Fork River, from water leaking in from the Clark Fork River. So this is the kind of study that you can do when you have enough information about the groundwater system. And again, we're interested in how the river system and the groundwater system are interacting. Now, Mountain Water Company also hired a consulting firm back in 2000 to do the same thing for all of its wells. And they did it in a two-dimensional model, which is not as complex as a three-dimensional model, but that doesn't matter. Take a look at this, right? So here's a well, and this yellow tracing of flow lines is basically coming back and showing you where the water is flowing from that's being captured from that well. And so if we look at that, we'll see that, well, the wells on this side of the river, Rattlesnake Creek underflow leakage and some Clark Fork River leakage. Of course, up here in the Rattlesnake, it's coming from Rattlesnake Creek Valley underflow. The ones up here in East Missoula, Clark Fork River leakage. The ones all on this side of the Clark Fork River, underflow from Hellgate Canyon and the Clark Fork. So this gives you an idea of the sensitivity of our groundwater system, our well system, to the groundwater system and the source of the water that's coming. It's coming from groundwater that's seeping out of the river system and going into the groundwater and moving towards those wells. So it's quite significant, right, thinking about managing the system, right? So if we go back to our question now, so we'll finish with this, and that is, how do we protect the quality and quantity of our groundwater system? Well, obviously, we got to protect the quality and quantity of water in the rivers, or we're in big trouble, right? So if the Clark Fork River chemistry, if we have a tanker truck flip over and go in the river upstream, we just better hope it goes through Missoula really fast, right? But if we change the chemistry for a long period of time, we're going to change the groundwater chemistry, right? So that's the take-home point there. How about protecting the quantity? We need to maintain water rights, right? Because the water rights are involved with this particular system. It gives permission to take that water in Montana law. Aquifer management. Can we put up safety zones around the wells where we don't want certain things to happen so they won't contaminate the wells? We have some of that in place already. Response, and how are we going to respond if somebody spills something onto the street and it heads to one of those storm drains? Or we have an industry and we release something we don't want released. How are we going to respond to that to protect our system? And then finally, there is one thing that's sort of out of our control, and that's drought. If the river levels go down, the amount of leakage goes down. And so our supply starts to get less and less as we have less and less water in the river. So that's something that we need to think about too. What are we going to do if that happens? How are we going to compensate for that? Okay, last thing. And this is just now we're at Milltown. Another application. How do the river systems interface with what's gone on up in Milltown? Okay? So that's our next question. And it says groundwater impacts resulting from the removal of Milltown Dam. So let's take a quick review of Milltown just so that we're on the same page. The site history, here's the dam, the original dam that's now gone. 1907, 1908. 1908, there was this giant flood. They had to blow the dam up, and it overtopped the dam, had to rebuild the dam. So it's really been in place since about 1908. And since that time, up to about 2000, sediment has been coming down the Clark Fork River and the Blackfoot River and collecting in the reservoir. So this is the Clark Fork arm of the reservoir. This is the Blackfoot arm of the reservoir here that backed up the Blackfoot River. In 1981, they discovered arsenic concentrations in community wells over here in the town of Milltown. The concentrations were about 500 micrograms per liter, and that was way above drinking water standards. And then there was about 25 years of work on studying issues associated with Milltown. And then in 2006 to 2011, the dam was removed and there was restoration on the river itself. The cost of that is estimated between $100 and $140 million, right, to do that restoration. They excavated the sediment in the reservoir as well as removing the dam. So what's it look like? What are the issues there? Well, here's the issues that we were asked to look at particularly, and that is that there were all these red dots are domestic wells, so individual house wells all through here, and there are over 500 of them. And the question was, when we remove the dam, are we going to disrupt the water service to those folks? Are their wells going to go dry? And if they are, then what are we going to do about it? So that was the question, and we want to know before it happens. That was sort of what the questions were that we particularly were working on. But in addition, all of these orange-looking things are contaminated wells with arsenic. Most of them are monitoring wells. There are a few, again, water supply wells in the community of Milltown, but most of them are monitoring wells, and this just sort of shows you where there was contaminated groundwater associated with the reservoir site itself too. And that was one of the goals, was to remediate the groundwater as far as removing the dam. This is what the arsenic plume looked like, the contaminated groundwater before the dam was removed. It was all underneath the reservoir sediments, and then it went out into Milltown, went underneath of the Blackfoot arm of the reservoir, that's here, and worked itself downstream to where this big turnaround or this big on and off ramp is down here. So it extended down about that far in the system. Again, what does it mean that drinking water standards were 10 micrograms per liter? How do we put that number in perspective? 10 pounds of arsenic and 120 million gallons of water. That's what that concentration is. So it's a very low concentration, but deemed to be hazardous if you drink it at higher rates than that. So EPA and DEQ wanted to mitigate any potential groundwater impacts before they happen. And so they wanted to know how much are the levels going to change and what actions do we need to do to fix things. So what we did is that we compiled the history, groundwater history, river history of the area. We then started a new monitoring program of water levels and river levels. We built and executed a numerical model of the system to help us generate the prediction of what was going to happen when they removed the dam. And then we looked at developing a decision tree. So once we had the results, what are we going to do? How do we make a decision? And then we're going to take action. So that was the plan as far as how we were going to proceed. So what do we think was going to happen? Well, what do you think is going to happen if you remove the dam, right? To the groundwater. Water levels are probably going to decline, don't you think? Because when they built the dam, they put 30 feet of reservoir head or height of water in the behind the reservoir, it backed up the river, and probably the water levels rose. We have no idea because we don't have any pre-dam groundwater data. But then when we take the dam out, we expect that the river will change and the water levels will most likely decline. And the question is, how much and where will they decline? So let's look at the quick geology here. We have, again, these valley aquifer system here. It's all sand, gravel, boulders, and clay up the Blackfoot, all the way up to Tora Bridge, all the way down to Hellgate Canyon. And there's basically none of that arid environment, 50-million-year-old stuff there. It's all coarse-grained sand and gravel. It's sitting on bedrock. So it's bedrock sides and bedrock boundary. So that's what the groundwater system looks like. Here's what the groundwater flow system looks like. Here's a Tora Bridge area up here. The blue arrows represent sort of direction of groundwater flow, and it's going into the stream up here, and it's coming out of the stream. So we have gaining and losing sections of stream up above the reservoir. And then once we get to the reservoir, funny things start to happen. The groundwater just seems to go like right underneath of the Blackfoot arm and continue its way down and head towards Hellgate Canyon. Same thing on the Blackfoot River. So we're going to have to figure out how the streams are interacting with this to be able to figure out what's going to happen when they take out the dam. So this is the groundwater system. And then we went out and did intensive study on the bed of the river trying to figure out whether it was gaining or losing or doing nothing. And so what we did experiments all along the river, out in the river itself. This was our field vehicle over here. We had red circles mean that we found losing reaches, losing conditions, and blue meant we found gaining conditions, right? And so what we did is that we found that we had sections of gaining and losing up above the reservoir, and then the reservoir was losing water. It was way above the water table, and the Blackfoot Arm was way above the water table. Fascinating. And down below the reservoir, the whole Clark Fork River was perched above the water table. Where's the water coming from and where is it going? What's the source of recharge to the aquifer? The recharge in red here was leakage from the Clark Fork River, leakage from the Blackfoot River, and leakage from the reservoir itself, right? 84% of the water coming into the system was from leakage, and then some water underflow up here at Tora Bridge. And then where was it leaving the system? Way right, Hellgate Canyon, right? It's the water we see coming into Missoula. So it was leaving the system by going into the Missoula aquifer system. So here's what we ended up doing. We built this numerical modeling tool. We took all the field data, we put it inside the computer, we reproduced the conditions, we matched them to what we actually observed. We had to divide the system up into discrete areas. We fed in all of our information that we had, and then we made a forecast. And the forecast was when we modeled it with the dam in place, and then we took the dam out numerically and said, okay, show us what's going to happen when we take out the dam. And so we then had a forecast. And the forecast, we took that, we put it into a decision tree, we then made a recommendation, and then there was an action or non-action taken. Okay? So here's what the forecast looked like. So it said if we take out the dam, this is the change in the groundwater system that's going to happen. So this is after we take the dam out. So interestingly enough, all the way down here into Hellgate Canyon, there would be a 3-foot drop in the groundwater level. And as we went back up, we'd have 6 feet, 7 feet, 8 feet, 10 feet. And then as we went on by here, we'd have 9, 8, 7, and then pretty rapidly, there's this whole section which has little effect at all. And that's that area where the stream's gaining and losing. It's really not influenced by the reservoir at all. And here is where we forecast, this is right under the reservoir, so that's the 2218 feet there. Okay? So that was our forecast. So what do we do with that forecast? Well, we said, okay, we're going to set up some criteria for whether or not we have to replace a well. So if this was the original static water level, and this was the forecast water level, then we said, is there at least 7 feet of water left in the well? If that's the case, then we don't have to drill a new well. But if there was less than 7 feet, we'd have to drill a new well because we just don't have enough water to produce, to keep that water supply going. And then the second question we asked is, if there was 7 feet, is there 4 feet of water above the pump that would give room to operate and to draw the water down to actually make the thing work? And if that answer was no, then we'd have to lower the pump. We'd have to physically go out and drop the pump deeper in the well. Okay? So that was really as simple as it was. So what did we do? So here's our forecast in map view. Right? This is just a piece of it that I tried to blow up so that you could see the dots. And so if we have a green dot here, that means that everything's okay. Don't have to do anything with that well. It met all of the standards, don't have to do anything. If it was black, like it is over here, or white, these black dots, then we have to drill a new well. So it met the conditions that we'd have to replace the well. Then if we had a blue or a light yellow dot, it meant that we had to lower the pump. So we had to go out and spend money and actually do something at the well to try to make sure they didn't run out of water. And then the final one was, heck, we don't know what's going on. We need to go out and check those wells. We just don't have enough information. So this is what the distribution looked like, and this is what the model's forecast first came out with. So it said 377 of the wells we wouldn't have to do anything with. 49 we'd have to replace. 10 we'd have to lower the pump, and 53 we didn't really know yet. And what we did is we did a series of models after the first run, and so we have a range of uncertainty from various scenarios that we were running to try to see how off we could be based on our decision-making process. Okay? So this is what the EPA and DEQ basically went on. They went on this map because they had to act quickly. They didn't want 5 years of information. They had to make decisions and start going out and doing things. Okay, well, what really happened? That was our forecast, remember? So what really happened when we look from we looked from 2006, which is this beginning point, to March 2010. And these are these are different colors, but here's 5 feet, 6 feet, 9 feet, 10 feet, 8 feet, 3 feet, 1 foot, less than 1 foot. And at each one of these wells, at this well, there was a 6.5 foot change in the water level from the beginning point. And in this well over here, close to the dam, there was a 10-foot water level drop. And in this well that was upstream from the dam, there was hardly any change at all, about 1 foot, 1 to 2 feet of change. Right? So this is what we observed. Well, now we better compare the two, right? So here's the simulated versus the observed. And you see that it's not too bad, right? I mean, it's pretty close as far as forecasting what we thought would happen in the system. So that was some success. So we were happy to see that, right? So what did EPA do with that information? Well, again, here's that map that we looked at here. And here's what we forecast, and they used to start replacing wells and doing things to try to keep people from running out of water. And here's what they actually did. Right? They looked at the data, and by the time when they were all finished, after 3 years of dam operations, of removal operations, 354 wells they said were okay. They replaced 81. They lowered the pump in 17, and they still had a bunch to check yet. Why is there a difference, such a big difference? Well, it's not too big because some of our estimates were way high for this, but it's because if people complain, they fix their well. You know, politically, they didn't want to have the challenge of the argument, so they basically fixed more wells than probably they needed to, but that kept people happy, and that cost you all $1 million. So there was $1 million spent to mitigate the consequence of the dam, of the withdrawal, the drop of the dam. Okay, so we're just about done, and I appreciate you staying as long as you have. Now let's look at the water chemistry. We were not tasked with looking at the water chemistry, which was a shame, but that's the way it was. And so I'm going to show you the results of what the before water quality data was on some of these wells they called compliance wells. These are monitoring wells, and then what it was after they removed the dam. Okay? So here's the distribution. That's the outline of the plume before the dam was removed. And these wells that I have here are wells that had very low concentrations of arsenic to begin with, pretty low, like 13 micrograms per liter, 25, 10, 13. And after the dam removal, they were below drinking water standards at these 3 places, and it was at drinking water standards at this one. So that was good. It went down. That was the idea. That's what we were hoping was going to happen. Right? And then if we look at the rest of these started out much higher. I'm sorry, I can see now this doesn't show up. This is 100 micrograms parts per billion. 750, and it went to about 15, went to about 14. This was 100, went to 20. This was 150, went to 50. This is these group down here. These were higher, but the good news was they were all trending in the right direction. So it didn't instantly fix it, and nobody thought it was going to instantly fix it, but it's going down, and that's what they hoped would happen when they removed the dam and took out all the contaminated sediments in the system. So we're basically done. So what do we know about groundwater systems? Where's it come from, and where's it going, right? What do we know about river systems? They're intimately connected to the groundwater. How about the Missoula Aquifer? How are we going to protect things? It's all about underflow and river water quality and quantity, right? And then finally, in Milltown, what were the consequences? We were able to forecast the physical reduction of water levels, and then there was a good outcome that the water chemistry was improving from what it was before the system. So I want to stop there, and I put this up because I said, well, you know, in my career here, these are my one group of graduate students that have either worked on Milltown projects or on the Missoula Aquifer projects. And so these are the graduate students, and then there was lots of undergrads, and then these are some of the funding agencies that helped us out. So I'm finished. I'm sorry I've taken so long, but I'm happy to answer questions.
Susan and Angela are going to have microphones as usual. So do you have questions?
Okay, thank you. No. Yes.
Based on information you have about how we're removing water from the aquifer and then how it's returned, would you say that the returns should be modified where and how, or is it done appropriately?
I'm not sure I understand the question. I think the question was if there, where water's being taken from the aquifer and then it's being returned, should we modify that somehow? Or is that? No.
Yes, the discharge from the sewage.
Oh, the discharge from the sewage. Well, you know, this is where I'm not a sanitary engineer, man. I don't know anything about that, you know. But
I mean, in terms of quantity of flows and where the
yeah, I mean, as you realize, every time you flush the toilet, it's got to go someplace, right? And it goes to the sewage treatment plant. And where'd that water come from? The Missoula aquifer, right? So what we're doing is recycling that water back to the sewage treatment plant, but it's not going back in the aquifer. It's going into the Clark Fork River, right? And it's so that leakage that's coming out of the Clark Fork River, part of it's being replenished by the time you get to the sewage treatment plant because we're returning a bunch of that water to the river, but it's not going to the aquifer. So it's not being returned to the aquifer. So we're taking that, my calculation of about 12% of the natural flow through the system and capturing it for water use. But some of it's going back into the Clark Fork River. And it probably is 80% or something like that. We don't consume that much water, actually. Other questions? Yes, Dave.
Just had that 12%. I wondered how that 12% number applied in other areas, say in the Bitterroot or in Phoenix, Arizona, or other places where there might be a water supply problem.
So as I understand, the question is, well, you know, my calculations are, say, about 12% for this, again, the eastern portion of the Missoula Valley. That was really where our municipal supply is being taken from. How does that compare to other places? Well, in other places, they're mining the groundwater, right? Like in Arizona. So if you're in Phoenix, they're actually taking out more groundwater every year than what's being naturally recharged. So that's why I kept going over these water budgets, right? Where's the water coming from? Where's it going? Well, in Arizona, there's very little recharge, and there's a great bunch of withdrawal. So the water level is dropping every year, and it's costing more and more to lift the water out of the ground because it takes more energy to bring that water from a deeper depth up to the surface. And they're eventually going to run out. It's like your savings account, right? You keep taking it out and don't put enough back in, it's eventually going to go dry, right? So that's why they import a lot of water from the Colorado River, too. Other questions?
So you've got aquifers with high rates of discharge and recharge and aquifers with relatively low rates. You said that the Missoula aquifer has about 75 billion gallons a year that comes out and presumably
goes in and comes out.
Right.
Yeah.
I'm wondering, in relative terms, whether we have a fast-flowing or a slow-flowing aquifer, i.e., is there an estimate of the total number of billions of gallons that's in the aquifer?
Oh, yeah, well, I didn't calculate that, but certainly we could do that. And that's just like, you know, a room full of bowling balls, right? If we know the volume of that water that's here in the bowling balls, all we have to do is subtract out the bowling balls, we can figure out how much water's in here. So we can do that. We can make that calculation. There's a lot of water in the system. Your other question was, is the Missoula aquifer moving quickly or things happening fast or slow? And the Missoula aquifer is really weird. I mean, it's not what you'd call a typical groundwater system because it's very coarse-grained. It's got these losing rivers, big rivers losing water feeding it, and water moves very fast. So the water in the Missoula aquifer from one area to the other, it's moving at velocities of tens of feet per day, and for groundwater, that's fast, right? The river moves in feet per second, right? Very fast, surface water. Groundwater, you know, moves much more slowly, but in this case, could be moving as fast as 60 feet a day. That's a very high velocity for any kind of groundwater system. But that's the Missoula aquifer. In a sense, it's a blessing because things are moving through it quite rapidly. Yes?
Where's the...
No, you're okay. Let's start here. We'll go back. Go.
What's the source of the Hellgate underflow? Where does that water actually come from?
Well, it comes from Milltown. Right? What's the source of the underflow? Well, where is it coming from? If we trace that back, it eventually, you know, goes back where it's just coming in from the mountains, coming in from the Blackfoot, leaking from the Clark Fork River up by Milltown, and then all that water is just moving down into the Missoula Valley. So it's coming out of the Blackfoot drainage, and it's coming above where the dam was, where there's exchanges going back and forth in the system, and then it starts losing a bunch of that water, and it's all being recharged up in that area there. Yeah, it's fat. Where's the underflow come? Well, it's coming from up there too, right? So it's not like it's a separate thing. Is there a question back here?
Who owns the aquifer, the water in there? Can
State of
somebody-
Montana.
State of Montana owns it? Are you
Yes,
sure?
sir. Yeah, state of Montana. So, Montana owns all of the water, and we only have permission to use it. So the state of Montana owns
And
everything.
It can't be, say, sold downstream by some company?
Water rights can be sold and bought and sold, right?
I
So-
know, that's a worry.
Yeah, but the water in Montana is owned by the state of Montana, and all you get, if I'm correct, and Tom can correct me, is a use permit, right, to use it. So it's still owned by the state. It's in the Constitution I have up here. So, another question.
I was wondering, are there closed basins where water doesn't flow, like the Wind River Basin or around Salt Lake, that there's not a
Yeah.
river that flows out?
So can you have a situation where it really is just a sort of a pool, But in reality, that's usually not the case. Even in Salt Lake, the water's recharged in the Wasatch Mountains. It comes down and feeds into the valley sediments, and it discharges into the Great Salt Lake, right? So there is a groundwater system that, again, goes from an area of recharge to an area of discharge. If you get deep enough into the Earth system, you could have very stagnant or almost non-moving systems, right, as you get deeper and deeper. But for potable fresh water, usually those systems are moving, right, and that they're not just sitting there stagnant water. We have aquifer systems, right, that form on the east front of the Rocky Mountains. The rocks stick out there, and then they dip down and go all the way out into central Montana. The Madison limestone, is that right, Don? You're going to help me back here. Yeah, okay. And so Big Springs, right, out on the Missouri River in Montana, that's a window into a big confined aquifer that's recharged in the east front of the Rocky Mountains, and it's flowing out across the state.
What kind of monitoring wells do you have below, or are there below the landfill, BFI?
There's a whole group. The question was, what kind of monitoring is there associated with, let's say, BFI, well, whatever it is now. It's not BFI anymore.
Republic, BFI.
Republic, the landfill. The first good news about the landfill is in the right place. And why is that? It's on that older stuff that's got lower water capacity, right? So it's up out of the valley floor. And a lot of the early dumps and landfills weren't. They were down on the valley floor. But if the question was, are there monitoring wells? And the answer is there monitoring. There's a whole group of monitoring wells. You can actually see them if you look for them along the interstate, on both sides of the interstate, because there is some, in the older cells that they built, they didn't line them or try to keep anything from leaking out of them. And so they're seeping, some of that contamination is moving very slowly out away and sort of down towards the valley.
So is it continuing to flow?
Yeah, yes, it's always continuing to flow, and unless they do something to stop it. And that might be turning on wells and pumping it, or it might be putting in some impermeable barrier, but that's not been done to my knowledge. The new cells are all being lined with liners and things to try to catch all of that and treat it and keep it from going into the groundwater. Any other questions? Well, thank you very much. Oh, Sandy, one more. What projects I'm working on now? Retirement. Thank you very much.